Hello, everyone, and welcome to lesson 10-3, which is on division properties of exponents. And this will be the last lesson in this chapter, so I will not cover everything. Chapter 10, division properties. And our objective, what we're learning, is how to divide powers with the same base. Just to recall what a power is, let's say I have a number, I'm making one up, 4, and I'm raising it to the third power. This is higher than the number 4. This is called a power. This right here, the 4, is called your base, and the 3 is your exponent. And the whole thing is called a power. And the way to evaluate that is you take the base and you multiply it by itself 3 times. So that's 4 times 4 is 16 times 4 is 64. When the numbers, the answers are pretty small, you can evaluate the powers. If they get too big, you just leave it as an exponent and base, okay? So today we're learning how to divide powers with the same base. It's always this base has to be the same, otherwise you can't do it, okay? And we're also going to raise a quotient to another power. And so in this base, we're going to write the rules or properties, and I'm going to give you the rules from the 2 previous lessons one more time, so you get them all in one place here, and you can always look that up. So the first one was to multiply powers with the same base. You add the exponents. And I'm shortening exponents, okay? To take the power of another power. You multiply the exponents. And to divide power, and this is all with the same base, so I left that out. Has to be the same base or it doesn't work. To divide powers. By the way, this one, yeah, there's no base. This one, yeah. To divide powers with same base. This is the new one. And what do you think? What's left? We subtract exponents. And I'm giving you an example here on that last one. So let's say you have 5 to the, I'm making a problem up, so 5 to the power of 3 divided by 5 to the power of 2. Notice we have the same base. So we can do that. We write the base one time and then subtract 3 minus 2, which is 5 to the first power, which is simply 5. And the reason this works is 5 to the power of 3 is 5. So I'm going to put why it works. 5 to the power of 3 is 5 times 5 times 5. And 5 to the power of 2 is 5 times 5. And you can cancel the common factors. And then what's left is just the 5. Okay. And then down here, they're giving you the same information again. Very same information. And here's the example that I just showed you why it works. 4 to the power of 5 is what? 4 times 4 times 4 times 4 times 4, 5 times. 4 to the power of 3, 1, 2, 3. You cancel out the common powers, and what you're left is 4 times 4, which is 4 squared, or 16. So this part right here, you don't always do, you simply subtract. 5 minus 3 is 2, and then you're done. And down here, it says the same thing again, one time in words. To divide powers with the same base, subtract the exponents in algebra using letters for numbers. Okay. Now, when you see a fraction, it means divide. Fraction means divide. Okay. All right, that's the first page. And second page, we're going to do problem 1C. So here we are, 1C. What is the simplified dividing algebraic expressions? What is the simplified form? And we're skipping to C. Okay, so I'm going to rewrite that a little bit bigger since it's so hard to see. It says k to the 6 times j, this is always times squared, divided or over k, j to the, what is that? 5th. Yep, j to the 5th. Okay, the k gets 1, right? When there is no power or when there is no exponent, you assume it's a 1. So the k's, I'm going to rewrite that separate so you can see it better. The k's belong together because they have the same base. One has 6 and one has 1. So that leaves me with k. 6 minus 1 is to the 5th. The j's go together. J squared over j to the 5th is, there's a times, this is turns into times. We have j as your base, 1 time. 2 minus 5 is -3. We don't want a negative exponent. This is a negative exponent. This is not. So I'll make a fraction and I put the j under it. So this right here is separate. And this 3 becomes positive and it's gone up here. So now what we have left is simply k to the 5th over j to the 3rd. These are different bases, so you cannot subtract the exponent. So this is our answer. Yeah. And then I wanted to do D with you. So now I have no more space, so I'm going to erase this. I hope you have your notes. So this part right here has got to go, okay? All right. I'll draw a line here so we have room. Okay, let me make that bigger. There it is. Okay, the A's have the same base, so those go together and the B's go together. So this right here goes together. So I'm going to deal with that first. I have -3 on the top, 5 on the bottom. So it's a -3 minus 5. You subtract the exponents, which is a to the -8. -3 plus -5 is -8. And then I'll deal with the B. The B is 7 minus 2, which is b to the 5th. And this is a multiplication problem now. All right, now we got to fix this negative power. So I'm going to put it underneath and it becomes positive. Gone on top. Simplify. These two I cannot combine because they are different bases. So that's my answer. Okay. So I'm going to write here no negative exponents in answer. Okay. Let's move on to the next page, 617. 617. So we're here. There we are. Okay, now we have another scientific notation. So I want to review that again. You can use the property of dividing powers with the same base to divide numbers in scientific notation. So I'm going to give you an example. I'm making up a number. I'll say 2.51 times 10 to the power of 5. So that means it's a big number. Positive exponent means the number is big. So I'm going to add some zeros. You can add as many as you want. I'm moving the decimal 5 times this number to the right to make the number bigger. 1, 2, 3, 4, 5. The decimal is now here. So then you're going to rewrite the number. And then you go from the back. After 3 numbers, you put a comma. That's not a decimal. That just makes you, the comma makes the number easier to understand. That's 251,000. And that would be the scientific notation. The same way, let me put it over here. So example 6.5. No, I don't want to use the same. I don't want you to think it has to be a certain way. Any number, 6.2 times 10 to the power of -3. The negative exponent means it's a small number. So I'm moving my decimal to the left. So I have to add zeros to the left. You can add as many as you want, but you're moving it 3 to the left. The decimal is here, 1, 2, 3. The new number is 0. So this 0 is this one. And then you have your decimal and then 0062. So this number is the same as this. Now, when you have the number here in front has to look like this. It has to have a whole number, the decimal, and then something else. This part right here can be bigger. Notice I have 5-1. It could go on, but the reason we want to write it in scientific notation is to, to keep it short. So therefore, you're probably going to round up or down, not to have too many of these decimal. In front of the decimal can only be one number. That's your tens. Otherwise, you have to fix it. Okay. All right, review. Dividing numbers in scientific notation. Well, it's going to be the same thing. They're always base 10. Scientific notation is always base 10. So they will have the same base. And what you do is you subtract the exponents. Same rule. The only difficulty is to understand the word problems. Okay. During 1 year, Honduras had a population of 7. Notice 1 digit, 0.33 times 10 to the power of 6. That's a big number. People. The area, so we have people and area of Honduras is 4.33 times 10 to the power of 4 miles squared. Notice you have miles squared here, and here you have people, different units. What was the population density of Honduras that year? It's people. The population density is people per square mile. How many people per square mile? The higher the number of people, the more dense or more crowded. Yeah. So this is density. How do you calculate population density? You divide people by square mile. Oh, by area, I should say, which is measured in square mile. Okay, so this is important for you to write down. Make sure you write your notes complete. So now let's write our fraction. So we have people is 7.33 times. The only time you see an X for times is during scientific notation. Otherwise, it's a dot or parentheses. So this is the only time. And then we have always base 10 for scientific notation, 10 to the power of 6 over the area. Yeah, the area is 4.33. 10 to the power of 4, and this is people, and this is miles squared, or square miles. Yeah, this is square miles. So now we have to divide. Use your calculator. You're going to divide this. And then use this to subtract power or subtract exponents. So 7.33 divided by 4.33 is about 1.69. Try it out. Times 10. 6 minus 4 is 2. So this is the amount of people per 1 square mile. And this number here is 169 per square mile. How do I come up with 169? 1.69 times 10 to the power of 2. Move your decimal 2 spaces. Yeah, the 2 tells you you're moving it 2 spaces. So this is your number. So if you have a square mile, let's say this is your map and you have a square mile, it's a square. That's how many people live in it, 169. So you can look up density of different places. Like, for example, Los Angeles, it's probably pretty crowded. In India, you have very crowded places. It would be interesting to find out. I'm going to look one up. I just looked it up in India, which I know is a very crowded country. In India, you have 1,000 something, I forget, people per square mile. And that is, when you think about it, that's on the average. So that's everybody spread out over the area of the whole country. So there's some regions that probably have no people because they're desolate. And then you have cities that are very crowded, but on the average, that's how many people would live there. It's not like that's exactly how many people live in every square mile. It's the average. On this page, we're doing the bottom also. And that's Saturn and Sun. And we're on page 617. The Sun's mass, I don't know what math, I'm not a good science person, but I know mass has to do with weight and volume, I think, how much weight per, anyways, look it up, but it has to do with weight and or volume, weight and volume. The sun's mass is 1.998 times 10 to the power of 30. That's a huge number. Yeah, you would have to move this decimal 30 times to the right to get and add a lot of zeros to get that real number. We're going to do it at the end, I think. No, maybe I didn't. Saturn's mass is 5.69 times 10 to the power of 26. Notice this number is bigger than this number, kilogram. How many times as great as the mass of Saturn is the mass of Sun? So this number, the Sun is bigger. And I know that because this number has more zeros. So I know when I divide, I'm going to put the sun over the Saturn, because it's easier that way in the end, because this is a bigger number. Otherwise, you're going to have a really weird looking decimal that you won't know what to do with. So put the bigger thing on top, divide by the smaller. Okay, so that's how it's going to be. So the sun has 1.998. I'm copying this number here, times 10 to the power of 30. And the Saturn is 5.69 times 10 to the power of 26. So you divide these two numbers. So 1.998 divided by 569, and then you round. You're going to maybe get a long decimal. You got to round up and down. We don't want too many decimals. My answer is 0.35, if I'm correct. I hope it is, times 10. Notice the base 10, same base. 30 minus 26 is 4, correct? Okay, now we have a problem. This answer doesn't work for me because we want a whole number here. This cannot be 0. So I'm going to move my decimal one spot to the right. Times. Now I have to adjust this 4. This 4 now is not correct anymore. So I'm going to give you a little hint, and I really need you to write this down because I get confused over this all the time. Do I add a number to 4 or subtract a number to 4? So here's the rule. If you move the decimal, which is this part, to the right, which we did, correct? To the right, then you subtract from exponent. So that means now from 4 turns into 3. Does that make sense? And then if there's a second part, because we could have to move it to the left, guess what? Add to exponent. However many you move it, that's how many you have to add or subtract. So this right here is a good piece of information to have, and I forget it every time. So this, hopefully you'll find it when you have to do that. And the reason I wrote that is you have to adjust the answer because it's not in scientific notation. You see that here? It's not scientific notation. You have to have it like that. Okay. So this right here. So how many times as great as the mass of Saturn is the mass of Sun? Well, this is how many times, but it doesn't make much sense. So what I'm going to do is rewrite it. When it's a small number, you can rewrite it to have a little view of if it makes sense. So it would be 3.5, add some zeros, move your decimal 3 spaces, 3,500. That's this answer, yeah? So now we can say the mass of the Sun is 3,500 times bigger than the Saturn's, than that of Saturn. So if you had Saturn over Sun, let's say this year you flipped it, you put Saturn on top and Sun on the bottom, your answer would look like this. And you would go, well, what does this mean? Well, then you have to say for the Saturn, the Sun is 3. So for me, it's always easier to divide the bigger number by the smaller number. Then I don't have to deal with a fraction like that. Okay, that's the only difference that you might say, well, why did she start with Sun? But remember, when you have a question like that, how many times does something go into the other? It's always a division problem. Okay. All right, let's move on. Yeah, on the next page. On the next page, we are doing a fraction again. And what you're ending up doing is, remember the word shower the power. So if you have a fraction, where are we here? Oh, this is just talking about how when you have a fraction and then parentheses around it, that means this is the base, and you have a negative exponent, all you have to do is flip the fraction. So if you go down here, this is kind of where it explains it. A over b to the power of negative n is b over a to the power of positive n. So all you do is flip the fraction. Negative exponent, flip the fraction. That's what this is about. So let's look at problem 4. What is the simplified form? Remember, to have it simplified, you cannot have a negative exponent, which there is. So simply this whole thing, because of the parentheses, this whole thing is the base. And all that is raised to the power of -2, which is not good. This is the part that is bad right here, okay? So what we do is we flip that inside of the parentheses. So you move the 5b on top and bring the a on the bottom, leave your, and raise that to, that negative becomes a positive. Don't forget that, okay? And then we shower the power. You take everything inside the parentheses and raise it to the power of 2. 5 squared b squared over a squared. And the only thing you can simplify is 5 squared, if that's 25. The b and the a are not the same base, so you cannot subtract exponents. So this is the answer, okay? Let's see if we have another one. The next page. Let's see where we're at. That's weird. Okay, next page. Nope, that's not what I'm looking for. Oh, yeah. Okay, yeah, that's it. We're done. So the next page is 619. I hope I didn't leave anything out. Nope. Okay, so we're on the homework. So simply do number 9. You same base, subtract the exponent. I'm going to show you this one. This is a little weird. Same base. You have y 3 minus 10. Well, 3 minus 10 is a negative exponent. It's y to the power of -7, which makes it 1 over y to the 7th. Or here's a way I reason this out. You got 3 on the top, you got 10 on the bottom. Who wins? The bottom wins by how many? By 7. And the top you got to replace with a 1. So you can also reason it out like that. Okay. So I've done number 9 for you. So now we're skipping to 11. And 12. And oh, there's another one. How many small cubes make a large cube? Okay, so this is another division. The large cube is made up of many small cubes. The volume of the large cube is, make sure the units match. Yes, they do. The volume of the small cube is blah, blah, blah. How many small cubes make up the large cube? So do large cube divided by small cube. If you do it the other way around, you will have a 1 on top of a fraction, and it's kind of hard to realize what's going on. But if you do it this way, it should give you a whole number. Okay, so now how many small cubes make up the large cube? Whatever your answer is. Yeah, that's it. Then you divide. And then we move on to 14 up on top. By the way, the word quotient, how is the property for raising a quotient to a power? Quotient is either a fraction or a division problem. So that's what quotient means, okay? To a power similar to the property raising. I already have something in my mind what I think I would say. Skip 15 down here. We're going to 16. And here you have to explain why each expression is not in simplest form. They're not in simplest form. You can fix it to make it in simplest form. Okay. It's just stuff you can do to make it shorter. You don't want any negative exponents, blah, blah, blah. You want to combine your same bases. This one is very, very interesting. Number 21. And what I did was I inserted you a slide on numbers, which is kind of, think about a plan. During 1 year, about 163 million adults over 18 years old in the United States spend a total of about 93 billion hours online at home. On average, how many hours per day? So we're changing units. You got to do unit analysis here, because here it was 1 year. So you have to figure out how many hours, this is hours, yeah. Hours, yeah. How many hours per day did each adult spend online at home? I want you to figure out how to write each number in scientific notation. Okay, how do you convert the units to hours per day? This is unit analysis, and I showed you that before. I want you to try it yourself and then see if you can figure it out. If not, we'll do it in class, but please try yourself. That's always the best. On this slide, oops, where is it? Where's my slide? I wrote some big numbers down. So the trillion, billion, million, you get confused over. So the trillion has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this has 12 zeros. So it is 1.0 times 10 to the power of 12. This is the number in scientific notation. And then this, so this is the prefix is tera. Giga is a billion. 369. So this is 1.0 times 10 to the power of 9. Million is mega. 1, so that's 6,000. That's 3 zeros, so it's 1.0 times 10 to the power of 3. Hecto, 100. 10 to the power of 2, and 10 is just simply 1.0 times 10 to the power of 1, if you want to. Deca, hecto, kilo. kilogram is like 1,000 grams. Okay, then we get to see how these numbers have positive exponents. Those are numbers. Now we get to the decimals. 0.1 in scientific notation is 1.0 times, so we need to move it this way, so 10 to the power of -1. This is a tenth. If it says round to the nearest tenth, your answer has to have a decimal and a number. Hundredth. This is where students get confused, rounding. How many decimals? There's 2. See? So that's 1.0 times 10 to the power of -2. Milli, 1,000th. Notice they all have a TH at the end. TH at the end means it's a decimal that's less than 1. Okay. Micro, 10, 1, 2, 3, 4, 5, 6. -6, 1, 2, 3. Yep. And then a nano is a billionth of a second. A nanosecond is the billionth fraction of a second. Ooh, I heard that before. In a nanosecond. So now let's count. I have to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. All right. So this chart should be helpful for this last question right here, down on the bottom. Think about a plan. And I believe that's it for this lesson. Good luck to you guys. I'll see you later.